like everyone, I want to thank our organizers, Joseph, Gordon, and Michelle, for organizing a meeting in this beautiful city, in this beautiful lecture hall. This is by far the nicest lecture hall that I've ever given a talk in. So thank you for that. Thank you for organizing this meeting. I'm going to talk about non-equilibrium quantum dynamics and quantum sensing with large trapped ion crystals. These crystals are formed and controlled in a penning ion trap. Penning traps are not as well known for quantum information processing as the linear RF trap, and you'll see there's a good reason for that. We don't have near the same control of individual qubits that the linear RF trap has. But I would like to emphasize that penning traps are good for controlling large ion crystals and crystals in 2 as well as 3D. So what can we do with these large crystals? Well, there are a couple directions. One is quantum simulation. Just like in the RF traps, we can engineer long-range Ising interactions. We can do quench experiments and benchmark non-equilibrium quantum dynamics, generation of entangled states. And so far, we've done that in a regime where we can benchmark with theory. And I'll give a brief summary of this work, but I'd like to focus most of my talk on a quantum sensing experiment where we sense very weak excitations of the center of mass mode of this single plane trapped ion crystal. Trapped ions are sensitive detectors of weak electric fields, and a potential long-term application of this is to use trapped ions as sensors for weak electric fields from dark matter. If there's time, I'd like to, in our setup as well as Brian Sawyer's setup at Georgia Tech Research Institute, we're working on ideas to introduce single-site rotations into our system, and I'd like to briefly summarize some of those ideas. So just to set the stage, this is a cartoon sketch of our penning trap. We shine in lasers, we image the laser-induced fluorescence. In this side view image, you can make out what looks like a single plane crystal, and then in light scattered parallel to the magnetic field, we can make out the individual ions that make up the crystal. These are beryllium ions separated by about 15 microns. And up front, I'd like to acknowledge the people who have done the work in the lab. These are students and postdocs from the last 10 years, which have pushed this work forward. And we really rely heavily on a collaboration with a long list of good theorists. So here's an outline of what I hope to talk about. Penning traps are well known in atomic physics, but we use them in a regime where the space charge fields are strong compared to the trapping fields, which is a little different than many applications of penning traps where people are trapping single particles. So I'd like to start by talking about how many ion confinement works in a penning trap. I'll describe our system. With trapped ions, we have 2 degrees of freedom to play with. It's the qubit degree of freedom and the motional degree of freedom. I'll describe what those are in our high magnetic field trap, and then our main tool is a spin-dependent force, which enables quantum simulation and sensing experiments. I'll then describe this quantum sensing experiment. This experiment uses time reversal to sense below the standard quantum limit, and this theme of using time reversal to enhance metrology we'll also hear about tomorrow in a talk from Vladimir Vuletic. And if there's time, I'll talk about how we can introduce single-site rotations into this system. So let me talk a little bit about how many ion confinement works in a penning trap. The confinement, so this is a cartoon sketch of our penning trap. It's just a stack of cylinders. And confinement in this direction is clear. We put a few kilovolts on these end cylinders relative to the central cylinder. We get a deep axially confining potential near the center of the trap given by this expression. So this trapping frequency, omega z, characterizes the strength of the confinement. That's about 1.6 megahertz in the work I'll describe. But you can see that the radial confinement is actually radially deconfining. The lowest energy state is for the ions to hit the walls of the trap. That doesn't happen because we immerse the trap in a strong uniform magnetic field, 4.5 Tesla. And so charged particles in this radioelectric field an axial magnetic field undergo an E cross B drift, which is a rotation about the symmetry axis of the trap. And as the ions are rotating through the magnetic field, they experience a V cross B induced Lorentz force, which points radially inward. So this means that our trapping potential, which is radially deconfining in the lab frame, is radially confining in the rotating frame of the crystal. This omega r is the rotation frequency, omega c is the cyclotron frequency. This is the V cross B induced Lorentz force, which is giving us the radial confinement. So the take-home message of this slide is that these crystals are rotating. They necessarily have to rotate to give us radial confinement. And it's something we need to control. And we do that by applying a rotating potential. In the community, we call this the rotating wall. And that's what these azimuthally segmented electrodes are for. And the fact that we can use time-resolved imaging techniques to obtain images of the ion crystal in the rotating frame of the rotating wall means that we have accurate phase lock control of this ion crystal rotation. So in my talk, I'm going to focus on work done with these single plane crystals, but I'd like to highlight that penny traps are really good for forming large 3D crystals as well. Ion crystals form as a result of Doppler laser cooling and the ions wanting to minimize their Coulomb potential energy. They're examples of strongly coupled one-component plasmas, which Tom Killian talked about yesterday. The type of crystal that forms, though, depends on the size of the crystal and the shape of the crystal. This shows a cartoon of different crystal shapes we get as a function of the rotation frequency. And for modest rotation frequencies here of a few hundred kilohertz, we get 3D crystals where this is work done many years ago, where we can detect body-centered cubic crystals when we have a few 100,000 ions in the trap. I'd like to comment, I think one of the reasons these large crystals are easy to generate in a penny trap is not just that we use static fields, but the non-thermal motion in this trap is a rigid body rotation, which doesn't couple very readily into the internal degrees of freedom. If we lower the rotation frequency, we get weak radial confinement compared to the axial confinement, and this is where we can trap single plane crystals up to 500-600 ions, and I'll be talking about work with single plane crystals up to about 200 ions in my talk today. So for those of you who are experimentally oriented, just show a quick picture of the trap, and I want to emphasize that this is at room temperature. This is a room temperature experiment. The trap's mounted here at the bottom of this long tube, and then it gets inserted into this is a room temperature vertical bore of a superconducting magnet. And this is an NMR style superconducting magnet that has good magnetic field homogeneity and stability. I'd like to highlight that there are other groups investigating the potential for penny traps for quantum information processing. Richard Thompson's group at Imperial College has done some nice work demonstrating control of different configurations of ion crystals, in particular this linear string along the trap axis. Mike Biersik's group has a setup similar to what I'm going to describe, and they've recently been able to demonstrate single-shot detection in the rotating frame of the crystal. Brian Sawyer has a nice compact permanent magnet setup, so it's a lot smaller than this large magnet that I just showed you. And then Jonathan briefly mentioned in his talk on Monday that he's starting a project on arrays of penning traps. This is a very novel project. I'll be looking forward to seeing how this works out over the next couple of years. So for many of these penning trap experiments, our qubits are Zeeman qubits. In Michael Biersik's experiment and ours, we're working with beryllium ions, and our qubit is the valence electron spin in the ground state of beryllium. In the 4.5 Tesla magnetic field, that's a spin flip frequency of 124 gigahertz. And then we have the standard techniques that all atomic physics uses, a nice Doppler cycling transition for Doppler cooling that also serves as a state detection. We typically do experiments where we optically pump and pair all the spins up. And we can do global rotations with resonant microwaves at 124 gigahertz. And in the language of quantum simulation, this is giving us an effective transverse magnetic field. The other degree of freedom we have to play with in trapped ion experiments is the motional degree of freedom. If we have an N-ion crystal, there are 3 N normal modes. And for the single plane crystals that I'm talking about, those modes break up into 3 bands. There are high frequency cyclotron modes, low frequency E cross B modes that describe motion in the plane of the ion crystal. And we use spin dependent forces to couple to these transverse drumhead modes. And you'll see why this is called drumhead modes in this video, which shows the calculation of the drumhead modes for 331 ion crystal. We got this from the Freerichs group. The highest frequency drumhead mode is the center mass mode, and as the wavelength of the mode goes down, the frequency goes down. So I'd like to advertise, but I won't talk about, that we can near ground state cool all of these drumhead modes with a technique called EIT cooling. So we use a spin-dependent force. This is the trick in ion trap experiments, to couple the spin and motional degrees of freedom. And in our work, that's a spin-dependent optical dipole force. We cross 2 laser beams at a relatively shallow angle and put these 2 laser beams at different frequencies, so it's a moving 1D lattice. And as the wave fronts of that lattice wash over our single plane ion crystal, the ions experience a spin-dependent force whose frequency is given by the frequency difference of the beams. And we can adjust laser parameters here so that the force and spin up is equal and opposite to the force and spin down. So this is the interaction we engineer. If you recall back to Monday's talk, Jonathan talked about an interaction which was an X sigma X, so it's very similar. This is what we call a light shift gate. Jonathan's was a Mulmer-Sorensen gate configuration. So this is the starting point for quantum simulation and quantum sensing experiments for us. In the work that we've done, we tuned the frequency of the spin-dependent force, this frequency mu here, very close to the frequency of the center mass mode. So this is showing calculations of frequencies of the higher frequency drumhead modes. For quantum sensing, we tuned resonant with the center mass mode. For quantum simulation, where we want to generate long-range Ising interactions, we tuned off. This delta is typically 1 or 2 kilohertz, while the splittings of the center mass mode to all these other modes are at least tens of kilohertz. So with this tuning where we couple just to the center mass mode, if we tune slightly off resonance, we realize a long-range Ising interaction. And in fact, if we only couple with the center mass mode, this is an effective infinite range Ising interaction. We can cast this infinite range Ising interaction in terms of what we've heard in several talks at this meeting so far, one-axis twisting or single-axis twisting. Here, S sub z is the z component of the composite spin of the system. And it's well known that the single-axis twisting at long times will generate a spin cat state. And I emphasize here that that time for generating this spin cat state increases linearly in the number of qubits in the system. So we have used one-axis twisting in quench experiments and have generated non-equilibrium quantum dynamics, generated entangled states, which we benchmark with theory. I won't talk about this work except to give a quick high-level summary. Basically, through measurements of spin squeezing and through measurements, we implement this multi-quantum coherence protocol, which enables us to measure at a time what are correlation functions. We can benchmark quantum dynamics up to about 10% of the cat state time. And this is for about 100 qubits in our system. Going forward, we'd like to increase the coherence of our interaction, as well as introduce complexity into the system. And one way we can do that is to implement single-site rotations. So now I'd like to move on and talk about this quantum sensing experiment. In this experiment, we sense very weak excitations of the center mass mode. One highlight I should mention before I get started here is that if we want to detect a weak electric field, there's an advantage to using an N-ion crystal versus a single ion. And that's because a weak electric field will excite the center mass mode of an N-ion crystal to the same amplitude as a single ion. In the protocol that I'm going to describe, we map that amplitude onto spin precession. And when we measure spin precession, our measurement of that spin precession improves as 1 over the square root of n because the projection noise goes down as 1 over root n when we measure this angle. So this is the interaction we're engineering. To see how this generates spin precession, let's consider that we apply a weak RF tickle to one of our trap electrodes. Eventually, we're going to put this resonant with the center mass mode, but for now, let's consider it's far off resonant from any modes. It's just going to wiggle the center of this trap a little bit. So we're generating some classical motion of amplitude z sub c, frequency omega, and phase relative to the spin-dependent force of phi. If I take this, plug it back into this interaction, you can see that I'm going to get a term which is a product of two cosines, and they're going to beat down and give me a term at this difference frequency. If I put the frequency of the spin-dependent force equal to the motional frequency, this is just going to give rise to a constant AC Stark shift across the ion crystal. That's going to generate spin precession at a rate given by the spin-dependent force, the amplitude of the motion, and then this cosine of the phase difference between the motion and the spin-dependent force. So there are two different protocols one can consider. One is a phase coherent protocol, where for each realization of the experiment, we can realize this same phase. That requires stabilizing the phase of the spin-dependent force. We've been able to do that in our experiment, and this is what I'm going to focus on in the rest of my talk. So measuring spin precession is straightforward. All atomic physicists know how to do this. We use a Ramsey technique. For us, we start with the spins up, we do a pi over 2 pulse, and then if we have a simultaneous application of the spin-dependent force, as well as this RF tickle, we'll generate spin precession. We then measure that spin precession with another pi over 2 pulse that rotates spin precession in the equatorial plane into excursions above and below the equator. We do our measurement in the z basis. So we can implement a known amplitude, measure the spin precession, and then repeat this experiment many times. And from this, we can answer the question, what's the signal to noise with which we can measure a given amplitude? And the answer is here. In one measurement, we can measure this off-resonant oscillation of 50 picometers. So in optomechanics, this type of experiment, which is done far off resonance, is usually is usually described as determining the measurement imprecision of this protocol. And so our measurement imprecision is 50 nanometers or 50 picometers. And to put that in perspective, that's about 40 times smaller than the ground state wave function of the center mass mode. Now, and I'll just highlight here that this limit is proportional to the off-resonant light scatter divided by the spin-dependent force. This is not optimized for our system, and there are certainly ions out there that can do a lot better than what we're doing here with beryllium ions. What we want to do now is to tune our drive-on resonance, but now the experiment gets more complicated because now we're going to be sensitive to thermal noise, we're going to be sensitive to zero-point noise, and to back action due to spin motion entanglement. So just to give you an example of the type of experiment we're thinking of, we prepare a motional state. Ideally, it's the ground state, and the measurement's going to show you it's actually a thermal state obtained from Doppler laser cooling. We then ring up the center mass mode amplitude. We create a coherent state. And then we apply the spin-dependent force. That's going to generate spin precession. If we crank up the strength of that spin-dependent force, we're going to start getting spin motion entanglement. That is, the wave function is going to break up into different spin states. And this is a form of back action because we only measure the spins, and if we have spin motion entanglement, the coherent length of our block vector goes to 0. Well, fortunately, we can use time reversal to get rid of unwanted spin precession and to get rid of this back action due to spin motion entanglement. And so we implement time reversal by inserting an application of the spin-dependent force before we ring up the center of mass amplitude. And in between these two applications of the spin-dependent force, we apply a pi pulse. This pi pulse transforms the composite spin of our system, f sub z, to minus s sub z. It changes the sign of the optical dipole force interaction. And so this is the time reversal part. It effectively undoes or cancels spin precession due to thermal motion, also due to zero-point motion, and will also undo the back action created by spin motion entanglement. So these spin-dependent displacements created in this first application are undone in the second application. I'll just briefly highlight that there's some nice theory work from Anna Maria Ray and her colleagues at how this protocol can be interpreted as a two-mode squeezing protocol. Here, the two-mode squeezing occurs for mixed spin oscillator coordinates, these coordinates p and x minus and p plus and x plus. This is a nice interpretation because we all know how squeezing works, so intuitively it's a very nice interpretation, but we don't know how to measure these, we don't know how to make a joint measurement of these mixed spin oscillator coordinates. But fortunately, time reversal undoes the spin motion entanglement, and we end up with a product state where the oscillator is displaced by some amplitude beta, and the spins undergo a precession by an angle which is proportional to beta. So let me show you some measurements. Here I plot our experimentally determined variance in measuring a small amplitude beta as a function of the application time tau of the spin-dependent force. One would expect that our sensitivity is going to improve with time. That's what these theory curves show. The red curve is theory without any decoherence. The blue curve includes decoherence due to off-resonant light scatter, and this goes down to about 40 times below the ground state wave function. And the ground state wave function size is our standard quantum limit here at a quarter. For short applications of the spin-dependent force, we get good agreement with this theory given by the purple line, but it deviates as this time gets longer. And the reason it deviates, this deviation is captured by theory that includes 40 hertz shot-to-shot fluctuations in the frequency of our center of mass mode. And so this frequency fluctuations of the center mass mode means that the time reversal is no longer perfect. Emphasize, though, that at this intermediate time, we're in a single measurement, we're measuring almost 9 dB below the 0-point fluctuations. And these experiments were done with just Doppler cooling, so we're canceling thermal fluctuations to 19 dB. So very briefly, and then I'll go to my two more slides. If we want to turn amplitude sensitivity into electric field sensitivity, we want to lengthen the time that we're bringing up the center of mass mode. And so we use two protocols here in this investigation. One is a stretched out version of the so-called quantum protocol, which uses time reversal in the previous slide. And then the other is this classical protocol that uses a single spin-dependent readout pulse. So this shows measurements of the experimentally determined uncertainty with which we can measure an electric field as a function of the total drive duration, this capital T, for both the classical protocol and the quantum protocol. I won't go over these in great detail except to point out that once again we can demonstrate substandard quantum limit sensitivity for these intermediate times. And if we look at these longer times, focus on these longer times, in a single measurement, we're sensing electric fields of a few microvolts per meter. And if we factor in our repetition rate, we're getting a sensitivity of around 240 nanovolts per meter in 1 second. Of course, this is at our center mass frequency of 1.6 megahertz. And we think this might be a record for an atomic electric field sensor. It compares favorably with this result of 5.5 microvolts per meter per second for a Rydberg atom sensor, which of course is at 10 gigahertz. So am I over now? Close. Let me just talk a little bit about the limits. This 40 hertz frequency fluctuations we think is due to finite in-plane temperature and the fact that we have some impurity ions on the edge of the crystal. So in other words, these ions are moving a little bit, and as they move, the center mass frequency fluctuates at this 40 hertz level. This should be a solvable problem. If we can solve this problem, the voltage stability will probably limit us at a few hertz. Theory shows us that with the frequency stability of 1 hertz and ground state EIT cooling, we could improve our sensitivity to this 10 nanovolts per meter per second. And at this point, the possibility of detecting electric fields due to dark matter becomes interesting. Using the axion as an example. So there are well-known experiments such as the haystack experiment and ADMX experiment, which sense gigahertz electric fields, or which are searching for gigahertz electric fields from axions. Here we're at a much lower frequency, and that changes our sensitivity because now we're in a regime where the axion Compton wavelength is large compared to the size of the region of our strong magnetic field. This is the bore of our magnet. And so our sensitivity for putting a limit on the axion-photon coupling is reduced to second order in the ratio of these two quantities. Nevertheless, taking this second order suppression into account, we think this 10 nanovolts per meter per second sensitivity translates into setting a limit of 10 to the minus 11 inverse GeV on the axion-photon coupling parameter. And that's competitive with current abracadabra and the base collaboration limits. The one thing I'll say is these experiments detect a magnetic field, and they are only hindered by this small quantity to first order. And of course, if we can do this experiment with 3D crystals, we can greatly improve our sensitivity, perhaps by a factor of 100. So if you want to talk to me about how we might introduce single site rotations, come and look me up. I'll just close by, I hope I've been able to illustrate that pending traps are a good system for forming and controlling large ion crystals for both quantum sensing and quantum simulation. We have lots of things that we're working on, which hopefully will lead to more powerful quantum simulations, perhaps variational quantum simulation. I'd like to highlight this paper from Ethreya Shankar and Anna Maria, where they show how we can explicitly take advantage of the rotation of the ion crystal to introduce or to generate chiral spin textures and simulate certain aspects of P-wave superconductivity. And then with quantum sensing, we'd like to extend this work to 3D crystals. So thank you very much for your attention.
Thank you very much, John. We still have some time for short questions.
So I get the impression that this sensor is pretty narrow band. How narrow band is it?
Yeah, so it's a narrow band in the sense that it's whatever you set your frequency, but then you would
you can
move your frequency.
Right, but it's single channel in that sense.
Right.
But so when you set it, how narrow is it?
Well, so the length of this experiment goes a few milliseconds, so that would set a bandwidth
I see.
of
So there
a couple hundred hertz.
Okay,
something like that.
so there aren't natural limits, at least not at the level that you're looking. I mean, I was going to ask, like, is there damping, and what does that come from? But that's
At this few millisecond level, it's really Fourier transform limited. We have done experiment where we've tried to measure the ring down and get slightly different results depending on the day. But the ring down is more than a couple hundred milliseconds of the center mass mode. Now, another question can ask, the dark matter fields at these very low masses are expected to be fairly coherent and could have an effective line width, don't quote me on this, but I think as low as a few hertz, or at least 10 hertz or less. So there might be some advantage to going to
well,
longer
that was going
times.
to be my next question. Is this good or bad for a dark matter search? And it sounds like it's going to be good, except it'll be looking for a needle in a haystack, right?
It's like all dark matter searches.
Okay.
Another question? There is something in the middle which I don't see. Yes, please.
Thanks, John. There are two questions I had, actually. One related to the amount of time you can probe, and it seems like you didn't discuss anything about the off-resonant photon scattering due to your Raman beam, so I'd be interested to know at what level that will limit you.
Yeah, so let me just go back a few to make sure we're talking. Go back one more.
Yeah.
So you mean how long can we probe here before light scatter from those beams are going to reduce? And off the top of my head, I can't give you a very sharp answer now, but out to half milliseconds, it's only causing a very small reduction in the length of our black vector, less than 10%. But if we went for very long times, that could be an issue. There are other operating points for doing this experiment. So you know a lot of the details. We're tuning between the Zeeman levels of the P states. If we tuned outside, we could reduce the spontaneous emission level. So I don't see that as a fundamental limit.
Mm-hmm. And then the second question was, in the 3D crystals, you presumably start to have to worry about the wavelength of the standing wave versus the spacing of the lattice?
Yeah. So we would have to implement a different type of spin-dependent force. And the idea there is the Malmer-Sorensen technique gives you extra degrees of freedom. And in particular, there's the degree of freedom where we would send the carrier beam in one path and the two sidebands on the other path, and that would enable this type of experiment to be done in 3D crystals. So it would take a different implementation of the spin-dependent force.
The last question, but very short, please.
Yeah, this could end up being a dumb question, but in the drum modes, you showed the frequency going down as you increase the mode number. Is this an intuitive?
Yeah, so that's a good question, and it's a commonly asked question because this is what people will call anomalous dispersion. And the way to think about that is the trap is setting the frequency. That's giving the restoring force of the center mass mode. Now let's think of a mode such as this tilt mode, where part of the crystal goes above its equilibrium position and part of the crystal goes below. There's screening, so the restoring force from each side is now going to be partially screened by the other side of the crystal. And so that screening gives rise to a lower frequency. And as the wavelength gets shorter, the screening effect gets bigger and bigger.
Apparently, I'm not a promise keeper. The last question now.
I have a really quick question. I just wonder for the electric field sensing part, can it sense the electric field as a vector, or is only like a projection amplitude along certain direction?
So,
Also, the electric field sensing.
So the type of sensing we demonstrated is, we put a voltage on one electrode, so it's giving rise to an electric field which is parallel to the magnetic field. And For the case of axions, that would be the case as well. The axion generated field will be parallel to the magnetic field. In principle, I guess we could also sense electric fields perpendicular, but we'd have to use a different mode.
Yeah, thank you.
I'm not sure I answered your question though, so you can talk to me afterwards.
Okay, I guess we have to finish at some point, so let's thank Olga and John once more.